All right, welcome back to another episode of Science with Surbeck. Today what we're going to do is we're going to review ions, ionic compounds, and then be able to name some of those ionic compounds. So a couple of objectives I want you to be able to accomplish is to be able to define the terms ion, ionic bonds, and ionic compounds, understand the guidelines for naming and writing the formula of ionic compounds, and then also be able to write the names given the formula of certain ionic compounds. So let's first start out here with what is an ion. And an ion is defined as atoms or a bonded group of atoms with a positive or negative charge. And so there's two different kind of ions that we need to be aware of. One is a cation, and these are defined as positively charged ions. And now these positively charged ions, they have this positive charge because they lost electrons or they gave away electrons. Now the other type of ion we have to be aware of is an anion. And an anion is defined as a negatively charged ion. And they became negatively charged because they gained an electron or electrons. And so with those things in mind, we can get into the definition of what an ionic bond is. So an ionic bond is defined as an electrostatic force that holds oppositely charged particles together in an ionic compound. Now, these ionic bonds are going to form during multiple types of chemical reactions. And then our last definition that we have here is an ionic compound. And an ionic compound is defined as any compound that contains ionic bonds. So the big takeaway here, ions, they either gained or lost an electrons and they become either positively or negatively charged. We can classify those as cations or anions, and then the ionic bond has to form during a chemical reaction, and as a result, we obtain or produce an ionic compound. So now what I want to shift gears to is actually understanding how we write the formulas for ionic compounds. So we'll transfer to the next page here, and we'll go to the ionic formula guidelines. So when we write the formulas for our ionic compounds, the first thing that we have to have is that the symbol of the cation or the positive ion is always going to be written first. The second thing is that the symbol of the anion or the negative ion is always written second. And then the third thing is that if needed, we must include subscripts, which are small numbers to the lower right of our chemical symbols. Now, these subscripts are used to represent the number of ions of each element in an ionic compound. And then we need to be aware that if no subscript is written, it is assumed to be 1, or the number of ions present in the formula is assumed to be 1. Okay, so if we put these things to the test, we can find out what is the correct ionic formula between potassium and oxygen. And before we even get into details with this, what I'm going to do, I have a blank periodic table on the next page of notes, and what I want you to do is this. I want you to follow along, and I want you to write exactly what I write. So this right here that I'm about to write becomes the charge that each group of element obtains when they become an ion. So this first group, when it becomes an ion, it loses 1 electron and it forms a positive 1 charge. So every element from hydrogen all the way down to francium, when it forms an ion, has a positive 1 charge. Now, if we transition here to beryllium all the way down to radium, this entire group has a +2 charge. Now we're going to skip over the transition and the intertransition metals, and we're going to move to the group boron all the way through thallium and element 113. This group of elements forms a +3 charge. We move over to carbon all the way down to element 114, and we have to be careful because this is either a plus or -4. Now, the way we typically know if it is a plus or minus is if it is written second or first will determine if it's plus or minus. The group with nitrogen all the way down to the group here has a -3 charge. Group with oxygen all the way down has a -2 charge. And then the group with fluorine all the way down has a -1 charge. So the noble gases have a charge of 0, so that is something to note. So you can put this on your periodic table, and I would encourage you to do that. Or if you need a little extra help, what I've also attached in notes is the ion formula chart. So this right here tells us what is the charge of our most typical ions, and it includes a lot of elements that are found on the periodic table. Now, one thing that I have skipped over is the transition and intertransition metals, and that's because they have a varying number of electrons that are lost. So some elements actually have a couple different what we call oxidation states or charges. So anyways, let's go through this and get back to our example. So we want to find the correct formula between potassium and oxygen. So potassium, if we find potassium on the periodic table, it has the element symbol K. So I'm going to first write K down. And I also want to look up what is the charge. And so K is in that first group. It has a charge of 1+. And then I move on to oxygen. And again, same thing. I find the symbol for oxygen to be O. And so I write down O. And the symbol for oxygen is a 2-, or the charge is 2-. Now, this is really important because I really didn't describe it in the directions, but when we do this, what we have to do, we have to cross the charge number, we have to swoop it, and that becomes the subscript for the other element. So for example, we always start here with our negatively charged ion, and we swoop it over, and so this means that we need 2 Ks. So we have K2, and we do the same thing over here with potassium. We take the charge and we swoop it to make it the number of ions we need of that element. Now I'm going to use purple so we don't get confused here, but we need 1 O. Now, to emphasize this, I'm going to write K2O1. If we look at our rules, it says, hey, no subscript written. We assume it to be 1. So what this formula becomes is K2O. Now, notice this. Notice this. I wrote the positively charged ion, the cation ion, first, which was potassium, followed by the negatively charged ion, or the anion. That is really important as we move forward. So again, remember the periodic table, remember that ion formula chart to help you understand those charges of those elements. So now what we are going to move on to is just doing the reverse process, and that is going from the polyatomic ions, which add another little extra rule into our particular set of circumstances here. So we'll transition here and we'll go to polyatomic ion formula writing. So with our polyatomic ion formula writing, the first thing to remember, poly is many atoms that make up an ion, and I'll show you that here in a second. But for this particular changes here is this: the charge is given to a polyatomic ion that is going to apply to the entire group of atoms. So I added there just the definition of polyatomic ion, and then I just stated the charge of the given polyatomic ion applies to the entire group of atoms. So let's take example here, our PO4, which is phosphate, and it has a charge of 3-. This charge of 3-, so I'm going to say 3- charge, applies to PO4 as a group. Now another thing to note is that the entire polyatomic ion is acting as one single ion or one single unit. The other thing that is really important, major difference here between polyatomic and normal atoms, is this: the subscript of the atoms within the polyatomic ion are never changed. So if you need more than one of those polyatomic ions, you place parentheses around that ion and write the appropriate subscript outside the parentheses. Again, if more than one polyatomic ion is needed, place parentheses around and write the subscript outside of these parentheses. So we'll do this in this example. So now we want to know what the formula for the compound form between the calcium ion and the phosphate ion. So calcium is an individual element, and so if we take our periodic table that we just labeled and we find calcium, element 20, calcium has the symbol Ca. And what you could also notice is that if you went up that column, calcium has a charge of +2, and we're going to write it as 2+. Now, phosphate, you could look on the periodic table, but I'm going to save you some time here. It is not on the periodic table. It is a polyatomic ion. Now, to help you out here, I do have another chart that lists some common polyatomic ions. And if you look on the 3- charge, you will find phosphate. And it's hard to see here on the computer here, but phosphate has the formula PO4 with a charge of 3-. So again, PO4 with a charge of 3-. Now what we're going to do the swoop-de-loop here, and so the charge number becomes the subscript for that opposite ion. So the charge number of PO4 is 3. So again, you do your swoop-de-loop here. That means we need 3 calcium ions. So we just write Ca 3, and I want to point out this. Because calcium is an individual element, we do not need parentheses. Now, if we go over here and we try to find how many PO4s we need, what we do is we take that charge number, and again, we do the swoop-de-loop, and I'm going to put way outside here. So this means that we need 2 PO4s. So to write that formula correctly, because we need 2 PO4s, we put in parentheses PO4. Notice how that is the same formula, and because we need multiple of these phosphates or these PO4, what we do is we put outside the parentheses a subscript of 2. And we did that because we needed more than one of these PO4s. Now, again, always double check here. Your calcium, or excuse me, your positive ion, which is calcium, should be written first, followed by your negative ion, and this is how we should write it. Now again, parentheses, only because this is polyatomic and we needed more than one. So this would become our formula for a calcium and phosphate ion. Again, that helps you out there. Those charts help you orientate things correctly. Now what we are going to do is we are going to transition to go from formulas to actual names. So now we'll have formulas and names in our video here. So, naming ionic compounds. Our guidelines here is this. Number one, the cation, or the positive ion, is always named first, and then the name of the anion, or negative ion, is given second. Now, the second thing that we need to get to is naming the cation. So, if we are working with an element, we strictly use the element name. So an example here is sodium. So if we have sodium and it's written as Na in our formula, what we would do, because it is an element name, we would just look up what it is on the periodic table, and we would find out that the name would be sodium. And all we have to do is write that name down. That's what the cation would become. Now there's one exception, and that is this. If the cation is a transition metal, the charge must be indicated in a set of parentheses. So an example of this would be iron 3+. So iron 3+, how it would be shown as Fe3+, and so it is a transition metal, and so what we have to think about is we write the name down, iron, but we also have to include the charge of this transition metal, and we do this by putting a set of parentheses, and then we have to indicate these in Roman numerals. So because it has a 3+ charge, the Roman numerals would be 3 lines, and so that would be iron 3+. Now we get to naming the anion. So the first thing with the anion is you're going to use the root of the element name. And then what you have to do is you have to chop off the ending and make it an IDE ending instead of the original element name. So let's go through an example here with naming an anion, and let's use the element Cl. So we have Cl, it's in the formula, it's listed second because it is an anion. And the first thing that we do is we look up our element name. So the element name for Cl is chlorine, and so all I'm going to do is write down chlorine exactly how I see it on the periodic table. Now, we need to chop off the ending so that we can put on the IDE ending. So what we do, and it's different for each and every element, but typically the last few letters, the last 3 letters sometimes, we chop off and we tack in IDE. So when we rewrite this particular name of this anion, it becomes chloride. Now, the final thing that we have to do is if the compound contains a polyatomic ion, we are just simply going to use the name that is given for that polyatomic ion. So an example of this would be if we came to the cation NH4+. Again, it's polyatomic because this whole set of atoms has that single charge. And to help you out here, all you need to do, one of the help sheets that I've given you here is you find NH4 and you write down the name exactly how you see it on one of these charts. So the name here for NH4 becomes ammonium. Now another example here would be something like OH minus. So again, another example would be OH minus. And if you would come to the chart, you would find OH minus, and OH minus, the name of that is hydroxide. And again, you just write down the name that you see listed here. So this would become hydroxide. We don't change any endings because it's polyatomic. So let's go ahead, let's put this to the test, and let's name some of these compounds. And that's what I have on the next sheet of paper. So we have NaBr as our first element that we need to name. So the first thing that we do is we identify what is Na. So if you find Na, it's element 11, and the name of that is sodium. Now the rules for naming the first element or the cation is always just write this down. So I'm going to draw a line that this is sodium. And then we have to ask ourselves, is sodium a transition metal? Does it span in this box or an intertransition metal? Answer to that is no. So we don't have to worry about the charges. Now, what we have to do here is this. We have to now look up Br because that is our next element listed. So Br has the name of bromine. Now, bromine is the second element listed. So we have to modify the ending because it is a anion, and so we chop off the ending and we add IDE. So for NaBr, when we go to name it, I'm going to name it out to the right here, it becomes sodium bromide. And that is the name for NaBr. Now we get to KOH. So the first thing here is you need to identify what is the positive and negative thing. And I will tell you that under most circumstances, the only polyatomic ion that we commonly deal with is ammonium. So if it's not ammonium, that means there's only a single element. So I'm going to help you out here, and I'm going to divide K and OH. So we look up K. And so K, if you find it on the periodic table, is the element for potassium. And so all I'm going to do is write down potassium. Again, we do not need to modify the ending, but we also need to ask ourselves, is K a transition metal? Is it found in this block of 10 or block of 14? The answer to that is no, so we can move on. Now, OH. There are multiple atoms in OH. That means it's polyatomic. So it's really nice for us. We just find OH, and the name of OH is hydroxide. So out to the side here, I'm just going to write down hydroxide. And because it's polyatomic, we do not have to modify that. We can leave it exactly how we found it on the sheet. So out to the right here again, I'm going to write down KOH's name, which is potassium hydroxide. And it's as simple as that. Now we come down here to our third example, and that is CuNO3 2. So the first thing here, that should be a dead giveaway that I know where my polyatomic ion is. That's because it's in parentheses. So what we do here, that's a dead giveaway. You can make your dividing line right there. We need to look up what is the element Cu. So we look for Cu. The element is copper. And then the second question that we have to ask ourselves is this: is copper one of those transition elements in these middle blocks? The answer is yes. It is right smack in that middle. And so what that means is we are going to have to indicate the charge in parentheses for copper. So what I'm going to do to help us out is I'm just going to leave a blank set of parentheses, and then we'll get back to this. Now, we have NO3, and we have two of those. And so our NO3, because it's polyatomic, all you need to do is you need to look up on our particular sheet, and you need to find, well, what is the charge for our NO3? Well, NO3 has a 1- charge, and the name of that is nitrate. So again, because the name is nitrate and it's polyatomic, it's really nice. All we need to do is write down nitrate. Now, we're not quite done because I said we have to decide what is the charge of this copper ion involved in this particular formula. So what we do is this. For our copper, we pretend that this is like a variable in math. And so I'm going to call my copper an X. And then we have to add to it the total charge of NO3. So the way we do this first is we identify how many NO3s do we have. So we have 2 times the charge of NO3. So the charge of NO3 is a 1-. That's what our chart says. So we take 2, which is the number of NO3s, times -1, and then remember this: all ionic compounds have to have an overall charge of 0. Okay, so we set this equal to 0. Now what I'm going to do is I'm going to have X plus 2 times -1 is -2 equals 0. And so if we consolidate, X minus 2 equals 0. We move this 2 over, we add 2. Our X becomes a positive 2, which what this means is that this is the charge of copper. So what we can do in parentheses is we can insert the charge of copper to be a Roman numeral of 2. So when we go to rewrite this, and I'm going to write it below, the name of CuNO3 is copper 2 in parentheses, and then nitrate. Okay, so now we have one left. We have Ag2CrO4. And so for this, we first again identify where is our positive from our negative. And again, I'm going to help you out here. If it's not NH4+, it's probably just a single element. So we have Ag2. So we look up Ag on our periodic table and we find it, and the name of Ag is silver. So we have silver, and then we ask ourselves, is it one of these elements in the middle? Yes, but I want you to hold tight. There are 2 elements that we do not give a set of parentheses to if it's in the middle. So I want you to write this on your periodic table. The first element that we do not give a set of parentheses to is silver. So you can put no parentheses for charge. It is always going to be for Ag. Ag is always a 1 plus charge. Always. The other element that we do not put a set of parentheses for in our transition metals is zinc. Zinc, again, no parentheses to indicate that charge. Zinc, when it is in its ionic form, it always has a 2 plus charge, and so that is why we never have to indicate what the charge is of zinc and silver. So yes, these are transition metals, but we do not need to indicate in parentheses what the charge is. So that's really nice for us. We don't have to worry about what the charge is. We don't have to deal with that parenthesis business like we did in that previous problem. The other thing is we have CrO4. Now, CrO4, we have to identify what that is, and because there's multiple atoms in that particular ion, we come over and we have CrO4, and you notice here that that is chromate. So the name of Ag2CrO4 is silver chromate. Again, there is no parentheses for silver because it always has a +1 charge. All right, so this concludes the review of ionic naming and formula writing. I hope you have enjoyed this video, and as always, subscribe.